Hello guys, welcome back to my channel. Today we'll be using the GeoGebra software to examine the sin x graph. So let me go right ahead. And if you look at my x-axis here, you notice I went up by pi over 2. So we have pi over 2, pi, 3 pi over 2, and 2 pi. Alright, this actually reflects the quadrant that goes up by, so the first quadrant is 90 degrees, then 90, then 90, going all the way up. On my y-axis, we have 1 and we have -1. So if you were to manually plot this graph on a graph paper, you could use a similar scale, and in order to get the values of y, we simply just sine the values of x, which is what I have here on my x-axis. So I would sine 0, I would sine pi over 2, I would sine pi, I would sine 3 pi over 2, I would sine 2 pi. Alright, so you can actually look at the graph between -2 pi and 2 pi, which is what is normally asked for in some cases. In other cases, they may restrict the graph to -pi and pi, depending. So you actually have to look on the domain that is given before you decide to sketch your graph. Alright, so let me put in the graph of y equals sin x and see what happens. This is my graph. Now we can start by looking at the amplitude, which is a displacement away from the horizontal. And the horizontal in this case is my x-axis. Now if I go up here, and of course this is referred to as a crest, especially for persons who do physics and look at waves, my maximum displacement here is 1. And if you look below the horizontal as well, you have it as -1, but my displacement is also 1 going down there. All right, so my amplitude is 1. All right, now let us look at what we call the period of this graph. So we have, and the period looks at when we have one complete wave or before the graph starts reproducing itself. So let us start at 0 here, 0, and my angles are in radians here. So we have 0, we have a crest, then we have a trough here, and then we start having a crest again at 2 pi. So we have one complete wave between 0 and 2 pi. So the period of this graph is equal to 2 pi. Let us summarize a few things. Now, notice what I did. I will shrink the graph a bit because we're going to be looking at different translation of the sin x graph. Going back, we said that the amplitude was 1, and the amplitude, we said that was the displacement from the horizontal. Now, because my amplitude is 1, notice here that my maximum value is 1 and my minimum value is -1. Notice also we have a maximum turning point there, and we have a minimum turning point down here at -1. The sin x graph is also important for solving equations. So for instance, what if I gave you an interval to solve sin x equals 0, and the interval is between 0 and 2 pi respectively? What I would be looking for is all the parts on the graph where when I sine the graph I get 0. So it is when the angle would be equal to 0 here, as you can see. When I sine pi, I get 0 as well. And when I sine 2 pi, I get 0. So trying to solve the graph of sin x equals 0 between 0 and 2 pi would actually give me 3 angles. So it's very important in solving trig equation, especially when sin x is equal to 0, 1, or -1, as you can see from the graph. Now, let us try to modify this graph. What if I were to multiply the graph by 2? What would happen? So what if I'm going to go over to my input bar here and put in y equal to sin x. Wow. Let us look at the amplitude now. Here my amplitude is 2. So it's almost as if I multiply the y value by 2. So my maximum value is +2 and my minimum value is -2. Now looking at 2 sin x, let us look at the period. If we look between 0 and 2 pi, we notice we have one complete graph there. So the period is not affected in this case. The only thing that is affected is the amplitude. So the maximum value now becomes 2 and the minimum value is -2. And just look to further explore this concept. Let us look at the graph of y equal 3 sin x. Alright, here it is in purple. The period is still the same. So the only thing that is affected is the amplitude. My maximum value is 3 and my minimum value is -3. So when I have the graph of sin x, just for looking at a shortcut, we can actually look at the value in front of the sin x. and we know what the maximum value is, or what the maximum displacement is, and what the minimum displacement is as well. The period is unaffected by the graph. So if you were to attempt to sketch the graph of 3 sine x, we could actually just sketch the original graph, which is what we have here in green, where you have 1 as the maximum value and negative 1 as the minimum value. We could simply just rub that out and simply put 2 and negative 2. Similarly for 3 sine x, you could sketch the original graph of sine x, remove the 1, put 3, and remove the negative 1 and put positive 3. Everything else will remain the same. As you can see, the period is still the same. We are back to the graph of y equals sine x. We examine 2 sine x, 3 sine x. Now what we want to examine is y equals sine of 2x. If we look at the maximum value here is still 1, same as the original graph of y equals sine x. The minimum value is negative 1, which is still the same. But it would appear as if the graph has gotten thinner. So let us look at the period. Started from 0, we have half crest between 0 and pi over 2, and between 0 and pi we have one complete wave. So technically speaking, the graph has shrinked. So we have produced an entire wave in half the interval of the original sine x graph. Now there are some certain deductions that we could make from this as a shortcut or as a reminder to ourselves if we're looking for an easy way to remember it. When we had the 2 in front of the sine, it affected the y values. We had multiplied the y values by 2. But look at what happens now when I have the 2 inside the function where we have 2x. What happens is that the period has been halved. So the graph has been affected in a horizontal sense, where I'm actually halving the period of the original sine x graph. So all I did here was just simply, as a shortcut, to multiply the period of the sine x graph by a half. Now we're going to look at the sine of a half x, but because this seems jumbled, we're going to have to remove the sine 2x graph to do that. In blue here, we have the graph of, as you can see on the far left, y equals sine half x. Now the amplitude is still the same, but look at this graph. It's stretched out. It's almost as if I multiply the period. Well, actually, we multiply the period of the sine x graph by 2. Let us see. We start here at 0 again. So we have one complete wave between 0 and 4 pi. So the graph is stretched out. The new period is 4 pi. So to achieve this using the original sine x graph, I would actually have to multiply the period of the sine x graph by 2. Very interesting graph here. Now, since we have looked at the vertical stretch and we have looked at the horizontal stretch, we're going to look at the combined transformation and see what happens. So what if I were to plot the graph of y equal 3 sine of 2x? All right, let's start first with the amplitude. The amplitude here, as you can see, is 3. So 3 in front of the sine x would mean a vertical stretch of 3. In other words, we multiply the original y value, which is the original sine x value, which was 1 by 3, and negative 1 by 3. Now let us look at the period of this graph. We have 2x here, and you can see the period here, where we have one complete graph, is pi. So we actually halve the period of the original sine x graph. So if you were to use a shortcut, what you could simply do is to sketch the original graph where you have 1 as the amplitude. You could remove that 1 and put 3 there, and where you have negative 1, you could remove that and put negative 3. To achieve the horizontal stretch though, what you'd actually have to do is to halve the period of the original graph. What do I mean by that? If you look at the sine x graph in green, you have where you have pi over 2, you see that at 1. What I would have to do is move that point halfway, which means that it would go at pi over 4, and it would still be at 3 here. Right? So you actually halve the graph, which is not so difficult to do. All of these translations can be done from the original graph.